All right, so now let's look at factors that influence polymer crystallinity. So when we talk about crystallinity in these thermoplastics, the kind of the key elements for whether something can crystallize, and so we call that crystallizability. So it's kind of a funny word, but it needs to form into this very ordered structure in very specific places. And so, as you can imagine, um, how flexible the polymer is, because we know that it has that chain fold um, model. So the chains have to be able to flex to allow for that folding. So chain flexibility is important. But also, if it's trying to form into a very regular shape and a regular structure, chain regularity is going to be important as well. And so things like side group and stuff like that, we talked about how those can be arranged on a polymer. Um, so isotactic or atactic and so forth, right? That regularity on the chain is going to matter. So let's look at some of the different kind of classes or structures of polymers and see how that connects with crystallinity. And so we've talked about the linear chain, chain branch, um, cross-linked, and networked. So if we start at the chain polymers, we see that these are very likely to crystallize because these chains can align, fold over, so forth very easily. They're very regular for the most part, and so they can crystallize. Branched polymers are less likely to crystallize, or to a lesser degree, but we can still form crystalline polymers. Uh, and the reason here is that regularity, right? The branches kind of affect how regular the shape is, and therefore make it slightly less likely to crystallize. And then networked, this one may seem counterintuitive because it already looks like it's in a very regular shape sometimes, but in fact, those crosslinks make it very difficult because we've made the polymer less flexible, right? So these chains can't fold over and stuff on themselves as easily because of these crosslinks. And obviously, those crosslinks make it less regular because they tend to be kind of random in those positions. And so they tend to be less so. And when we get to the high cross-linking, so there's always a degree, right? So if there's a lot of cross-linking, then these would tend to be amorphous. And the same thing with networked polymers. Because they already have all of these covalent bonds, there's not as much flexibility in these structures, and therefore these networked polymers tend to be amorphous. So heavily cross-linked and networked tend to be amorphous, whereas linear, branched, and the low degree of cross-linking can all crystallize to varying degrees. All right, so again, it's governed by flexibility and regularity of the chain, and therefore the various aspects that can affect those would be the kind of the size and nature of the side groups. So the smaller the size, the more likely it is to crystallize. The bulkier, the worse. And same thing with like the electron rich groups and so forth. Um, Branching, which we just talked about, this affects the crystallinity. Tacticity, so how they're arranged spatially on a chain. And then also secondary bonding of the chains. So if there's stronger secondary bonds between chains, that can affect the possibility for crystallinity. So let's look at side groups first. So bulky side groups tend to limit the ability to crystallize because they hinder kind of the diffusive motion, right? They stop things from moving as easily, and so they affect the overall flexibility. They decrease it, and so they can't arrange as well. Same thing, bulky side groups can also make it less efficient packing because they don't allow things to come as close together. And so, so if we kind of look at two different groups, this kind of much bulkier group will affect crystallinity. And so if we're kind of comparing these two, then we would say this one is more likely to crystallize. And this one is less likely because of the large electron-rich group. All right, and again, branching can hinder crystallization, like we talked about, because it makes it less regular and stops things from coming together as easily. And this example, the kind of difference of branching, it plays itself out in the differences between low density and high density polyethylene. So LDPE versus HDPE. So if we look at the two, low density polyethylene is branched, so it has a modest level of branching, and it can crystallize to about 60%, and it has a density of 0.92 grams per centimeter cubed. So low density, so you're going to guess that high density is slightly higher. So low density, this is flexible packaging, tarps, Ziploc, think Ziploc bags. That's probably the most common one. Whereas high density polyethylene is only linear. So there's basically no to little branching. And so the crystallinity can go higher, and therefore the density would go up. So it looks like a modest increase, but that's a fairly sizable increase for a polymer. And so this is more structural, like milk jugs. So think milk jugs on this one. And so it really affects the properties. And so some examples, so packaging on both of these, and then more structural things like milk jugs, but also kind of toys and things like that can also be HDPE. All right, so chain regularity and tacticity can also influence crystallinity. And so regularity, these are the different tacticities that we saw, right? That tells us about their arrangements. So we saw that iso and syndiotactic were regular arrangements because they either had everything on one side, so isotactic, or they alternated syndiotactic. But both of those were very regular arrangements of those pennant or side groups. And so those are much more likely to crystallize. However, if we look at something like atactic, which is kind of over here and it's more random, right? We don't know where the side groups are going to be. It's hard for chains or parts of the chain to align with others because it's a very random structure. And so the different groups may be in a less favorable position, especially if they're very large groups. And so atactic tend to not crystallize to the same extent. And so polypropylene, that's true. There is no crystallization observed in the atactic form. And so atactic polypropylene really doesn't have any practical value. So we really do need isotactic or syndiotactic for those materials. And so in this case, again, if we're kind of comparing, this regular arrangement is what we want for crystallinity, and this random is not what we want. All right, so the last one I had on the list there was secondary bonding. And so this actually increases the driving force for crystallization, because if you think we now have a force that's wanting different chains or different parts of the chain to bond together. And so strong secondary bonds tend to increase that driving force for ordering. And the most important sort of an example of this is found in polyamides, which you might know as nylons. So this is nylon 6 here. And so these polyamides have the formation of hydrogen bonds. So effectively in nylon, you see this NH group. And so once we have hydrogen bonded with a nitrogen, we know that we can have hydrogen bonding. And so when we have the oxygen of the other part of the chain here, this wants to form a strong hydrogen bond. And we know hydrogen bonds are very strong. And so the propensity for these strong secondary or / hydrogen bonding makes these crystallize much more than ones that wouldn't have a strong secondary bond. So these kind of groups that we see in nylon really increase the amount of crystallinity that we can have. However, it can have an influence, other influences, so there's often a trade-off. And so the presence of these polar groups tends to increase the stiffness, and so they can be more brittle. All right, and one kind of last thing I wanted to mention here in terms of crystallinity is just the general molecular weight effect. So shorter polymers, like you kind of see here on the left, are more easily crystallized than really, really long ones. So there tends to be this kind of upper limit here where if we have something that has a really high molecular weight, really long chains, they tend to get kind of tangled. And so this tangling prevents crystallinity or makes it harder to crystallize. Whereas these are much more free to move around, so the flexibility and so forth. And so it's much easier for these to crystallize as opposed to really long molecular weight. So there's always this effect. So this one's going to be more likely to crystallize. And again, there's this kind of entanglement or tangling factor if we have really high molecular weight. So that's another one to keep in mind.